Jai Hind to all of you. I am Priyanka Sharma, Assistant Professor EC Department, AKGEC. I am going to present my video lecture in Fundamentals of Electronics Engineering, BC 101. So, in this subject, I am going to cover up the complex topic of Unit 5, Fundamentals of Communication Engineering. So, in this lecture, I am going to cover up the fundamentals of amplitude modulation. So, in earlier lectures, we had discussed about the modulation techniques. So, we had studied already about, we have different modulation techniques. Modulation is basically of two types. Modulation is basically two types. One is analog modulation and other is pulse modulation. So, this is the category of analog modulation. So, in analog modulation is again we have two types, amplitude and amplitude and angle modulation. We have again two types, amplitude modulation and angle modulation. So, in this particular topic, I am going to cover up the amplitude modulation details. So, first of all, we need to understand what is amplitude modulation. Basically, we know that we have modulation process in which we are going to modulate the low frequency carrier signal with the high frequency carrier signal. So, in this process, we have two signals. One is message signal called as modulating signal and other is carrier signal which is a higher frequency signal. So, if we are going to define the amplitude modulation, amplitude of the carrier signal is varied in accordance with the instantaneous amplitude of the modulating signal. This process is known as amplitude modulation. So, in this process, we have one message signal which is a lower frequency signal. This I am representing as MT, and I have another signal which is called as carrier signal, which is a high frequency signal which is represented as CT. So, if we are going to superimpose this lower frequency signal over the higher frequency signal, we will get the amplitude modulation. And this amplitude modulation process leads to the production of another signal called as amplitude modulated signal. Okay. So, in this we have amplitude of carrier signal which contains no information. As per the amplitude of the signal, at each instant it will going to have an information content. So, what we are doing the change in the amplitude of the carrier in accordance with the message signal. So, we are providing the content to the carrier signal. So, the carrier amplitude going to be varied linearly by the modulating signal which consists of range of radio frequency, and this frequency of carrier, this will not going to affect the frequency of carrier. Frequency of the carrier will remain same and it will be propagated with the carrier frequency signal. Now, next, if we see it diagrammatically, we can have two signals here. One is message signal, this I am representing as MT, and another is your carrier signal, that I am representing as CT, and the modulated signal I am representing as ST. This MT message signal I am taking as a sinusoidal input. So, I can represent this as in the form of equation as AM sin omega MT. Another carrier signal, I will going to represent this as AC sin of omega CT. So, I can represent here amplitude as AM. I can represent carrier amplitude as AC. So, after the modulation, we are going to obtain the signal like this. So, here what we can see here, we have this message signal with the blue line comes here. So, this message signal contained over the carrier, and we can see here this in carrier signal initially the amplitude remains constant, but after the superimposition of the message signal with the carrier signal, we can see here the amplitude of carrier got changes according to the message signal at each and every point at which instant the message is going to be changed. So in this way we can see here message is going to be overlapped with the carrier signal. It is in the positive side also or it is in the negative side also, because carrier we have positive amplitude also and negative amplitude also. So in this way we can see the message is going to be overlapped with the carrier signal in both the sides, in the positive side or in the negative side. So in this way we can say here negative side. We can say here the message contained in the carrier in two bands. One is called upper sideband, and other is called lower sideband. One is called USB and other is called LSB. And this we can say the envelope of the modulated signal. And in this case we can see here the maximum amplitude of the modulated signal is defined by the modulating signal. So this can be treated as maximum amplitude. This is called as maximum amplitude Vmax, and this is called as minimum amplitude called as Vmin. So we can see here from the graph the maximum amplitude can be calculated as AM plus AC, because it is the sum of maximum carrier amplitude plus message amplitude, which is AM here. And the minimum amplitude we can calculate from here as AC minus AM, because if we see the reference here, this is, what is this? This is your AC. This is my AC, and from this AC I have to subtract AM, then only I will get the minimum amplitude. So this is the amplitude modulated wave which is obtained from the amplitude modulation process. So this can be represented as ST. So now we are going to see the mathematical equation, or if we first going to see how we are going to modulate, what is the circuitry or electronic equipment required. We just have a simple circuitry. We have an input message signal. We have an input message signal here which is taken as either in the cosine form or in the sinusoidal form. And we have a carrier amplitude here, and we have a summer here which is going to add the two signals, message signal and carrier signal, and we get the SAM, that is the amplitude modulated output. After this I will get the amplitude modulated output. So let us see how this can be achieved mathematically, how we are going to obtain an equation which is for the modulated wave. So this is the modulated wave SAM. So here we can see the equations of message signal and carrier signal. Message signal is represented as AM cos of 2 pi FMT. Here I am taking the cosine signal, and we have a carrier signal which is taken as AC cos of 2 pi FCT, where AM and AC are the amplitudes of modulating signal and carrier signal respectively. FM and FC are the frequency of the modulating signal and carrier signal respectively. So we have an amplitude modulated equation which is represented by ST as we are modulating the carrier amplitude AC with message signal, or I can write one more equation here. ST is equals to carrier amplitude is modulated with the help of message signal, and it is transmitting with the carrier frequency 2 pi FCT. So this can be, if expanded, and can be written as AC plus message signal can be written as AM cos of 2 pi FMT, and we have carrier signal as cos of 2 pi fct. 2 pi cos of fct. So now if we are going to discover this, and I am going to again sum up the equation st equals to, taking AC as a common value, we will get 1 plus mu cos of 2 pi fmt and cos of 2 pi fct. What is mu here? I had taken AC as common value. So mu can be written as, mu is basically AM divided by AC. This is taken as mu is equals to AM divided by AC. So mu is basically called as modulation index. Mu is basically called as modulation index, or we can say it as a depth of modulation. So if I am going to split this equation again, so it can be written as AC cos of 2 pi fct plus AC mu cos of 2 pi fct cos of 2 pi fmt. So after this, if I am going to apply the trigonometric equations, we have cos of 2 pi fct and cos of 2 pi fmt. So here we can apply the trigonometric equation of 2 cos of A cos of B, which is given as, this can be written as, how I can write this? This is written as cos of A plus B plus cos of A minus B. So this equation can be used to expand this equation. We can expand this equation again in this way. So it can be written as ST or equals to AC cos of 2 pi fct. This is the first part we had, and another part we're going to expand with the help of trigonometric equation. So we can obtain as AC mu divided by 2, which is cos of 2 pi fc plus fm t, plus AC mu divided by 2 cos of 2 pi fc minus fm t. Now next we'll get the final equation like this. So again, this is the modulated wave equation. This is called as amplitude. This is called as amplitude modulated wave equation. Amplitude modulated wave equation. So how are we going to interpret this equation as? This equation is basically consists of 3 parts. We have 3 components here. First is containing AC 2 pi fct. This is completely carrier part. So this is called as carrier component, and other 2 components contain the message. That means we have fc plus fm in one part, and in other part we have fc minus fm. So basically we have 2 components which we had already observed in the previous graph. One is upper part and other is lower part. So this upper and lower part is basically well seen in case of frequency spectrum. This if we plot this as a frequency spectrum, we have one upper frequency component and one is lower frequency component. So this upper frequency component is called as upper sideband, and this lower frequency component is called as lower sideband. So basically we can say modulated equation has 3 parts: carrier part, lower sideband and upper sideband. Carrier part only contains the carrier frequencies, and upper and lower sideband basically contains the message signal. So we have message signal present in 2 bands, lower sideband and upper sideband. Now let us talk about one factor which I had told you, that is the modulation index. Modulation index in the previous case I told you is equals to AM divided by AC. This is the factor I had taken here. What is this modulation index? This modulation index is basically represented by mu or m, and this is equal to the ratio of amplitude of the message signal to the amplitude of the carrier signal. So we can calculate the modulation index by this formula by taking the amplitudes of the message and carrier signal. So basically, what does it define? It basically defines the extent of modulation, or we can say it defines the depth of modulation. By this, we can decide how much message signal can modulate the carrier signal, up to which extent the carrier signal can be varied in the amplitude. So this basically can be represented in this way. Also, this amplitude modulation index can be represented in another formula form, which is represented by the graph, that is maximum and minimum value of the modulated wave. So we have two values, maximum and minimum value, which is represented in the graph. This is the graph we have. This is the Vmax. So you can also represent it as Amax, or we have Vmin. We can also represent it as A minimum. Minimum amplitude and maximum amplitude obtained after the amplitude modulation. So if we take these two, minimum and maximum amplitude, we have maximum amplitude and minimum amplitude of the modulated wave. Now we can have the maximum amplitude if we take it in the form of amplitudes of message signal and carrier signal. We can write Amax as AC plus AM. Already it is represented in the graph. This is the combination of AM plus AC, and the minimum amplitude is equals to AC minus AM. So this can be represented in the equation form like this: A minimum is equals to AC minus AM. Now if we are going to add these two equations, and we can obtain from this equation AC. So AC can be written in terms of maximum and minimum value of modulated wave as Amax plus A minimum divided by 2. And by subtracting both equations, if we are going to subtract these two equations, we will going to obtain the value of AM in terms of Amax and A minimum, that is Amax minus A minimum divided by 2. So now the modulation index can be obtained as, by putting these values in the formula: AM equals to Amax minimum divided by 2 and AC equals to Amax plus A minimum divided by 2. So now the modulation index obtained here is A maximum minus A minimum divided by A max plus A minimum. So this is the another formula for modulation index, which can be obtained from graphical representation. So we had already defined the modulation index, or we can say it as the modulation depth. It is also called as percentage of modulation, and this can be obtained by just multiplying it by 100. So we have different extent of modulation. We have different type of modulation we can categorize in different way. So there is some terms regarding this. For a perfect modulation, the modulation index should be 1, which implies that we have 100% modulation. And if we increase the modulation index, the carrier experiences 180-degree phase reversal, and which causes the additional sidebands, and hence the signal got distorted. And this comes under the category of over-modulated wave, which causes the interference, and this interference cannot be eliminated. So we just want to avoid this. We does not want to increase the modulation index above 1. So we will either going to take the modulation index 1 or lesser than none. So this comes under the different cases of modulation index. So now next we are going to study about the different modulation index. So first we are going to have the modulation index. In this case we have the modulation index . In this case, first we are taking the modulation index case. this is the case 1 I am taking. In this case, m is lesser than 1. That means modulation index is less than 1. It signifies that if m is equals to am divided by ac, that means this shows that am is lesser than ac. That means amplitude of the message signal should be lesser than carrier amplitude. Only in that case, the modulation index will be less than 1, and this is the case of under modulation. And this is generally used for transmission of the signal, and this will be more preferred. So the modulation case we had referred here is basically the under modulated wave. So now next we have the value of modulation index. Let's suppose if it is greater than 1. So what happened? If it is greater than 1, that signifies that if m is greater than 1, this is the second case, and in this case am is greater than ac. And if am is greater than ac, so it will going to overlap into the another signal. So, or it will going to cross the axis. Here we are seeing here the message is going to cross the axis. So that means some part of the message is going to be lost. So this will going to interfere with the lower sideband. So this is the crossover modulation. This also can be called as crossover modulation. And this should be avoided because in this case we are losing our message. Now the third case is case 3. Case 3 I am taking as case 3. Third case, m is equals to 1. That means am is equals to ac. This comes under the case of critical modulation. This signifies that if I am going to change the modulation above this, if I am just going to change the modulation above this, it will going to be distorted. So in this critical modulation, I am going to obtain the signal just touching the axis, just touching the x-axis. So this is the case of critical modulation. So in this case, our am is equals to ac. So these are the 3 cases of modulation index. Now next, we are going to cover up some power calculations. So this power calculation we can consider here from the equation of the modulated wave. So we have the modulated wave equation. We have the modulated wave equation. In this we have 3 parts. This is the carrier part, this is upper sideband, this is your lower sideband, and these are the amplitude of, this is the amplitude of carrier part, this is the amplitude of upper sideband, this is the amplitude of lower sideband. So this can be best represented in the form of frequency spectrum like this. So if we first consider the carrier part, this is the carrier part. This can be represented at Fc, and this carrier frequency has amplitude which is equals to, if I am going to draw this for the amplitude, this is basically drawn for the power calculation. If I am going to draw it for the amplitude part, so this is amplitude and this is frequency, and let us suppose this is the carrier frequency Fc, this has an amplitude AC, and we have another 2 bands which is in the upper side and the lower side. Upper band is called as Fc plus Fm, and lower side band is called as Fc minus Fm, and these 2 have same amplitudes, mu AC divided by 2. This is also mu AC divided by 2. This is the frequency spectrum of the amplitude modulated wave. This is the frequency spectrum of amplitude modulated wave. So in this case, we had observed that this is the frequency spectrum, and in this case we can also obtain the bandwidth. This is the bandwidth. Basically bandwidth is defined as upper sideband frequency minus lower sideband frequency, and it is basically obtained as 2 FM. If we calculate this, we will going to obtain this as a 2 FM. Basically, this is twice of the frequency of baseband signal or modulating signal. Now, if we are coming back to this power calculation part, we have 3 components. So, in these 3 components, we have total power can be calculated as sum of the power of carrier, upper sideband, lower sideband. So, we have 3 powers: carrier power, upper sideband power, lower sideband power. So, basically in case of power, we are going to calculate the power with the help of RMS voltages. So, power is basically calculated by the standard formula, which is given as Vrms square divided by resistance. Resistance is taken as the resistance of antenna. So, we have this RMS value, which is given as Vm by root 2. Vm is the peak amplitude, or divided by root 2 whole square divided by 2. So, in our case, for carrier signal, we'll going to take Vm as Vc. This is for carrier signal. For upper sideband, Vm is taken as AC mu divided by 2. For lower sideband also, Vm is same, that is AC mu divided by 2. So, these are the peak amplitudes, and from these peak amplitudes, we will going to find out first RMS value, Vrms for the carrier, Vrms for the lower sideband, Vrms for the lower sideband and Vrms for the upper sideband. So, this can be calculated step by step. First, carrier power can be calculated. So, the carrier power, we had the carrier amplitude divided by root 2, and it is obtained as AC square divided by 2R. Now, for the upper sideband power, we have Vm equals to AC mu divided by 2. So, Vrms is obtained as AC mu divided by 2 whole square, Vm square divided by root 2. AC mu divided by 2. That means we have AC mu divided by 2 root 2. So, this is the Vrms value for the upper sideband. So, by substituting these RMS value and by putting into the formula, we obtain the upper sideband power as AC square mu square divided by 8R. The same power will be obtained for the lower sideband. So, this is the lower sideband we had obtained, which is AC square mu square divided by 8R. So, after this, we can calculate the total power of the AM wave by adding all these 3 powers: carrier power, upper sideband power and lower sideband power. So, by adding these 3, we will get the combined equation as total power is equals to AC square divided by 2R. I am taking this as a common factor, 1 plus mu square by 4 plus mu square by 4. So, this is going to sum up and we will going to get the equation as 1 plus mu square by 2, and this AC square by 2R part can be represented as PC, that is the carrier power. So, this is equals to PC multiplied by 1 plus mu square by 2. So, this is going to represent the total power of AM wave. So, basically what does it signifies? It basically signifies my AM signal is going to be transmit with whose total power is represented by this equation. So, we can see this formula and we can calculate our practical system by calculating this power, how much power we want to transmit. So, on the basis of this, we can design our communication system. So, this communication system can be designed easily with the help of this power calculation. So, this is showing the power spectrum or power calculation of EM wave, and we have this spectrum. So this is the power and frequency spectrum. Earlier what we had drawn, same this is for the carrier signal. EC square by 2R we get. For lower sideband, MC square P naught by divided by 4, and upper sideband we have M square P naught divided by 4. So let us end up here. So we're going to continue this power calculation or this related numericals in the next lecture. Jai Hind to all of you.